The ground beneath your feet is a liar. It feels solid, dependable, and still. You build your home on it, you park your car on it, and you assume that unless a catastrophic event occurs, it will remain motionless. But this stillness is an illusion, a sensory limitation of the human body. In reality, the Earth is shivering. It is vibrating, cracking, shifting, and humming in a ceaseless symphony of motion that never sleeps. Every single day, millions of tiny fracture events ripple through the crust, invisible to our senses but screaming to the sensitive ears of modern technology. These are micro-quakes, the invisible tremors that make up the vast majority of seismic activity on our planet. For decades, they were dismissed as background noise, the static on the radio of geology. But today, a revolution in seismology, driven by artificial intelligence and fiber-optic sensing, has turned the volume up. We are discovering that these tiny ghosts hold the secrets to predicting volcanic eruptions, monitoring climate change in real time, understanding the deep internal structure of Mars, and perhaps one day forecasting the catastrophic big ones that level cities. Welcome to the hidden world of micro-seismicity, where the silence is deafening. To understand a micro-quake, one must first grasp the terrifying scale of seismic energy. The Richter scale, and its modern successor, the moment magnitude scale, is logarithmic. This is a concept that is often misunderstood. It means that a magnitude 7.0 earthquake is not twice as strong as a magnitude 6.0. It releases 32 times more energy. When we talk about microquakes, we are generally referring to events with a magnitude of 2.0 or less. A magnitude 2.0 earthquake releases about as much energy as a construction site blast or a lightning bolt. It is rarely felt by humans unless they are sitting perfectly still directly on top of the epicenter. But the scale goes down much further. A magnitude 1.0 quake carries roughly the energy of a small hand grenade. A magnitude 0.0 event releases the energy of a large man jumping off a table. And yes, earthquakes can have negative magnitudes. A magnitude -2.0 is roughly equivalent to a brick falling from a scaffold. The scale is relative to a baseline, not zero energy. With modern instruments, we can detect a quake as small as a fracture in a rock the size of a smartphone deep underground. While the catastrophic quakes grab headlines, they are statistical anomalies. For every magnitude 7 quake, there are 10 magnitude 6s, 100 magnitude 5s, and so on. By the time you get to microquakes, there are millions occurring every year. The Earth's crust is in a state of constant, granular adjustment. It is not a solid block of concrete. It is more like a pile of sand under pressure, with grains constantly slipping, settling, and grinding against one another. The challenge in studying these tremors has never been their existence, but their detection. The Earth is a remarkably noisy place. Ocean waves pounding against coastlines create a constant hum, known as the microseism, which is distinct from micro-earthquakes. Wind vibrating trees, atmospheric pressure changes, and human activity like traffic, subways, and heavy machinery create a chaotic din of background vibrations. For a seismologist in the 20th century, finding a microquake was like trying to hear a pin drop at a heavy metal concert. But the 21st century brought us noise-canceling headphones for the planet. The explosion of knowledge regarding microquakes in the last 5 years is largely due to two technologies: artificial intelligence and distributed acoustic sensing. In the past, identifying an earthquake on a seismogram was a manual task. An analyst would look at a squiggly line and pick out the P wave and S wave. This was time-consuming and prone to error, especially for tiny signals buried in noise. Enter deep learning. Algorithms like QuakeFlow, DeepShake, and CondNet-Quake have been trained on millions of confirmed earthquake signals. They do not get tired, they do not get bored, and they have superhuman hearing. In a landmark study applied to Southern California, researchers fed an AI historical data from a particularly active decade. The human catalog listed about 35,000 earthquakes. The AI reanalyzed the same data and found 1.8 million earthquakes. The fault lines had not changed, but our ability to see them had. The AI revealed that faults previously thought to be dormant were actually sparkling with microactivity, tracing out hidden geometries deep underground that human analysts had missed entirely. Perhaps the most sci-fi advancement is distributed acoustic sensing, or DAS. Traditional seismometers are expensive and difficult to deploy, but the world is already wrapped in millions of miles of fiber-optic cables, the backbone of the internet. By shooting laser pulses down these cables and measuring the backscatter of light, scientists can detect microscopic stretching and compressing of the fiber. This effectively turns a 10-kilometer cable into an array of 10,000 individual seismometers spaced 1 meter apart. In cities like Palo Alto and Tokyo, DAS is being used to monitor micro-tremors beneath skyscrapers without digging a single hole. On the ocean floor, unused dark fiber cables are now recording microquakes in the deep sea, filling in a massive blind spot in our planetary surveillance. However, not all invisible tremors are natural. In fact, one of the most urgent fields of study involves microquakes caused by human industry. We are no longer just observers of the Earth shaking. We are conductors. Hydraulic fracturing, or fracking, involves injecting fluid at high pressure to crack rock and release oil or gas. The fracturing process itself creates thousands of microquakes. This is intentional. These tiny cracks allow the hydrocarbons to flow. However, the bigger issue arises with wastewater disposal. When the used fluid comes back up, it is often injected deep underground into porous disposal wells. If this fluid lubricates an existing stressed fault line, it can unlock the fault, turning a microquake swarm into a damaging macroquake. Oklahoma provides the starkest case study. Historically, the state was seismically quiet, but between 2010 and 2016, following a boom in wastewater injection, Oklahoma became the earthquake capital of the United States, surpassing California in the frequency of magnitude 3.0 plus events. The sequence was almost always preceded by clouds of microquakes, invisible warnings that pressure was building up in the basement rock. Similar lessons have been learned in the pursuit of geothermal energy. Enhanced geothermal systems promise clean, limitless energy by pumping water into hot, dry rock to create steam. But fracturing that rock requires inducing seismicity. In Basel, Switzerland in 2006, a geothermal project induced a swarm of thousands of microquakes. The operators monitored them closely, but the magnitude ramped up faster than expected, culminating in a magnitude 3.4 earthquake that rattled the city, caused millions in damages, and shut down the project permanently. In Pohang, South Korea in 2017, a similar project triggered a magnitude 5.4 earthquake, injuring dozens and displacing over 1,000 people. These disasters have pivoted the industry toward traffic light systems. Operators now monitor microquakes in real time. Green means proceed. Amber, which signifies an increase in microquake magnitude or frequency, means reduced pressure. Red means stop immediately. The safety of future green energy relies entirely on our ability to decode these invisible tremors. Far from the industrial centers, in the frozen wastelands of Greenland and Antarctica, microquakes are telling a different story, one of climate collapse. Icequakes are seismic events caused by the sudden movement of glaciers. They occur when ice cracks, when a glacier lurches forward over bedrock, or when a massive iceberg calves into the sea. In the early 2000s, seismologists noticed a strange new class of signals coming from Greenland. They were not tectonic. They were glacial earthquakes, generated by massive slabs of ice, some the size of Manhattan, sliding into the ocean. But beneath these giants lies a constant chatter of micro-icequakes. These tiny tremors allow scientists to track the velocity of glaciers in real time. As surface ice melts due to global warming, water trickles down to the base of the glacier. This lubricates the interface between the ice and the rock, causing the glacier to speed up and slip more frequently. The frequency of these microquakes correlates directly with atmospheric temperatures. A spike in microtremors in a glacier is often the precursor to a major calving event. By listening to the ice crack, we are hearing the physical sound of sea level rise. Seismology is no longer earthbound. The study of microquakes has become our primary tool for exploring the interiors of other worlds. Between 1969 and 1977, seismometers left by the Apollo astronauts recorded thousands of seismic events on the moon. These included deep moonquakes caused by the tidal pull of the Earth stretching the moon's interior, and thermal moonquakes, a unique phenomenon where the lunar surface, baking in the sun, expands and snaps. These tiny tremors occur like clockwork every lunar morning, a morning stretch of the crust. More recently, in 2018, NASA InSight lander placed a seismometer on the surface of Mars. The planet is much quieter than Earth because it lacks active plate tectonics, but it is not dead. InSight detected hundreds of Marsquakes, mostly in the micro range. Many of these tremors originated from a geologically young region called Cerberus fossae, suggesting that Mars still has active faulting and perhaps even magma moving deep underground. By analyzing how these faint microquake waves bounced off the Martian interior, scientists confirmed for the first time that Mars has a liquid core. The silence of Mars is actually a blessing. Because there is no ocean noise and no wind noise at night, InSight could hear vibrations that were infinitesimally small, measuring displacements smaller than the width of a hydrogen atom. This brings us to the holy grail of seismology. If millions of microquakes happen all the time, do they act as a countdown clock for the catastrophic ones? The answer is the subject of a fierce scientific civil war between two theories, the cascade model and the pre-slip model. The cascade model suggests that earthquakes are essentially random domino effects. A microquake happens. Sometimes it triggers a slightly bigger one, which triggers a bigger one, and rarely the cascade runs away into a magnitude 8.0. In this view, the big one starts exactly like a microquake. It just does not stop. If this is true, prediction is impossible, because the Earth itself does not know which microquake will grow up to be a monster. On the other hand, the pre-slip or nucleation model suggests that before a fault ruptures, it slowly starts to slip, generating a specific pattern of microquakes known as foreshocks that signal the coming break. The 2019 Ridgecrest earthquakes in California offered a tantalizing hint supporting the pre-slip model. Sophisticated analysis after the fact showed that a distinct sequence of microquakes migrated along the fault days before the main rupture. They were unzipping the fault in preparation for the big break. The problem is that we only recognized this pattern in hindsight. The challenge for the next decade of AI seismology is to recognize these patterns in real time, to distinguish the preparatory microquakes from the millions of random background tremors. The study of microquakes has fundamentally shifted our perception of the planet. We used to view the Earth as a static stage upon which life plays out, interrupted only occasionally by geological violence. We now know the Earth is dynamic, fluid, and constantly talking to us. It speaks in the crackling of glaciers melting into the sea. It speaks in the rhythmic thrum of magma chambers filling beneath volcanoes. It speaks in the sharp snaps of rock responding to human fluid injection. And it speaks in the faint shivers of a fault line preparing to slip. These tremors are invisible to the eye and silent to the ear, but they are the pulse of the planet. By decoding them, we are moving from a species that survives natural disasters to one that understands the deep, intricate mechanics of the world we ride through space. The ground is moving. We are finally learning how to listen,